This podcast is sponsored by Click Playground. This free programming environment lets you explore and test your data-driven app ideas using Click's engine and APIs. The goal? Less query writing and more efficiency with associative indexing. Visit playground.click.com to learn more and see it for yourself.
Welcome to the InfoQ Podcast. My name is Wes Rice and I'm your host. In addition to hosting the InfoQ Podcast, I chair the QCon software conferences organized by InfoQ. Both InfoQ and QCon are organized around the idea of practitioners talking to practitioners, or more specifically, senior professional developers and architects talking to senior professional developers and architects. On this week's podcast, I talked to Yao Yu, who is a software engineer at Twitter. Much of Yao's career has been around building and optimizing caching systems like Memcached, or Twitter's fork of it, and Redis. Recently, she stood up a new performance team at Twitter, building on some of that work. On today's podcast, we talk about things like the charter of this new performance team, where and how you should be instrumenting for performance monitoring. We talk about things like metric aggregation and interesting problems at Twitter, interesting problems Twitter has seen around performance, including one involving Ellen DeGeneres, and some of those solutions, very elegant solutions to some of these problems, in fact. Thank you for joining us today on InfoQ's podcast. I hope you enjoy it. Welcome to the InfoQ Podcast.
Good to be here.
So last time we talked was at QCon London in March, and you were working on Pelican. You switched teams, right?
What happened exactly is I started a team. So I decided that what I did with cache, which a lot of which is performance work, is actually more widely applicable for a large array of workloads. So we started looking at all kinds of performance problems within Twitter. And we think the best way to do that is actually start a dedicated team whose charter is about performance.
Okay, so what's the charter? What's the team's focus?
So there are really two things. So one is to look at the infrastructure we have and focus on the performance problems that affects pretty much everybody or a large number of services or people and see what we can do to improve the performance there. The other thing is actually building infrastructure for performance. So when people start talking about performance, they want to see what can be improved and how. And the first roadblock they run into is they have no idea where things are bad. Right? So visibility actually leads to insight, and insight leads to improvement. We also want to be in the business of building the infrastructure that provides visibility, provides insight, and that will naturally lead to improvements to the system's performance.
What does that look like at Twitter? What does building performance monitoring or performance infrastructure look like?
I can give you a couple of examples. So the status quo is we do have monitoring. We do observe the health of hosts, so we do observe the health of services, and there is infrastructure to do that. On the other hand, the existing infrastructure has limitations, and those limitations are important or most felt when you want to debug performance issues. For example, there might be micro spikes in your traffic, but if you only have minutely metrics aggregated, those micro spikes, which last maybe 200 milliseconds, 100 milliseconds, that throws a bunch of failures or increase your P999 latencies, won't surface naturally on the minute aggregation or average. So that calls for higher fidelity into the monitoring. And that generally is not provided by a general purpose monitoring infrastructure. So there are certain requirements for performance monitoring that just not considered or available in the generic monitoring. Another thing is we are looking at the long-term trend of things. That only ties very loosely to performance. When we talk about performance, it's about latency and stuff. But overall, we also care about efficiency and capacity planning and things like that. So knowing the long-term trend, which is something if you don't care about the day-to-day, is not obvious to you. So if system performance degrade a little bit every time you push out a new deploy, like 1%, 2%, over the course of a long period, like a year or two, it can become quite significant. But a human operator, before and after the launch, won't notice the difference right away. If you look at the long-term trend, though, that should become more obvious. So we're also looking at ways to automatically generate trending data about the health and the efficiency and the performance of our services.
So is this a space of machine learning? Are you talking about trending? What's the scale or the scope of it?
We consider machine learning as one of the tools, right? Just statistics in general is what converts data into insight. But machine learning is a nice buzzword. I will use it if it gets me attention or if it gets me resources. But first is make sure we have data and we know the data is clean and this data is trustworthy. Second is to derive something that is more meaningful from the huge amount of data that we are like.
Congrats on the new team. One of the things I really wanted to do on this podcast was dive into actually monitoring and performance tuning at scale, because as I'll say here in a little bit, my experience is SSH into a box or 2 boxes or 10 boxes. But when you've got 10,000 boxes, that experience has got to be drastically different. So I want to ask about that. But before we do that, I kind of just want to set the stage and kind of talk about a bit about vocabulary and make sure we're just talking the same words. So when I talk about latency, there's a request come in or something like that, and I'm talking about the time that something takes to respond to it. Is that a good definition of latency? How do you define latency?
Latency is not a purely objective thing. People tend to think of latency as a measurement. In my opinion, latency is a collection of measurements or any number of measurements depending on where you are measuring. So, for example, if you have a service that has a fairly deep stack, you're using some framework, that framework depends on library, it may be running on a virtual machine, the virtual machine may be running inside a container, and then on some hardware connecting to a network, right? If you measure your latency at the very top of that stack, so the software inside your application is your request, it needs to traverse this very deep stack to get to the service you were talking to. So that latency will include all the slowdown and all the work that happens in the software stack, in the hardware stack, over the network, on the remote host, and back. So that would look very different if you're measuring this request as it goes out to the network. Like if you were sniffing the packet and you take timestamps as soon as it goes out and as soon as it comes back, I guarantee you there's likely a big difference between the two. So yes, what matters to application developers is probably the latency that they observe wherever they are interacting with the system. However, to make sense of where the latency is coming from often requires having multiple instrumentation entry points. So if you want to know whether it's because your local stack is slow, or whether it's the remote service that is slow, or the network is glitchy, you will have to insert other monitoring entry points to break down your top level activity.
Okay, but what do you recommend here? I mean, we're in a new world where we're deploying, say, a JVM application into a containerized environment, right? We don't necessarily have that visibility into the rest of the stack so that we can have that holistic latency across the entire response. How are you tackling these problems with internal teams that happen to see some kind of performance problem in their service?
I would say if you have a concrete problem, so what we have done, I can tell what we have done in the past. We have in the past have customers who are using JVM and therefore they have a GC cycle here and there in their application, coming to us with perceived latency numbers that are very high because they observe that in their application. And what we do to help them break down whether it's a client-side issue or a server-side issue is we start monitoring traffic on the host. So we use things like TCP dump or whatnot to capture the flows that corresponds to the traffic sent by the application. And we compare those numbers with the numbers that the clients are observing at the top. And there is a huge discrepancy in this particular case. And we realized that most of the latencies actually came from within the JVM as compared to everywhere else. So I think depending on the exact setup of the stack, sometimes you can reach down a little bit into the stack, right? You're using a library, so you can maybe instrument the library or the library does that for you. You can turn that on and say, at a lower level in my software stack, what am I observing? Is that the same or similar to what I'm doing in my application? And if you have control of the box, you can do it on the system side as well.
So it's challenging to deal with the different layers of abstraction, right? Between an AMI and a container and the JVM that's operating. How are you dealing? What are you doing to instrument at each of the different layers?
It's hard to be very thorough about this. It's actually fairly difficult to instrument layers you don't control, like you're not a developer. I think this should only be done when there is a need. And that's why tools like TCP dump is great, right? You can come in and apply it when there's a problem. And usually you don't turn it on because that's fairly expensive.
Right. But is this what you're building on your team? Is that these different layers so that application developers deploying a service, but your team is handling all the different layers or dealing with these? Is that kind of the scope or the infrastructure?
So our scope is more about finding out outliers in our system. Of course, we can do instrumentation on a case-by-case basis for people. But I think when you have a large-scale operation, what tends to happen is 99% of your instances or 99% of the time, all your services run just fine. But there is one hotspot somewhere, one slow instance somewhere, one machine that seems to be throttled all the time or is sending a huge amount of traffic and causing reliability issues. And these are difficult to surface when you have 10,000 instances running simultaneously. And again, another issue is earlier we were talking about the general monitoring infrastructure, right? Those tend to give you a fairly coarse view, a big picture view of your overall system. They are not very good at zooming in to one or a few of the problematic instances and give you a lot more information or finer grain information about them, because those are the interesting use cases. You cannot afford to collect everything at a finer grain, right? It's not necessary, in fact. So the ability to know where to zoom in and when to zoom in and having the flexibility to dial up or dial down your information collection provides a lot of value when it comes to chasing the outliers in your performance problems.
That's exactly where I want to get to is scale. But before we get there, you use some other phrases that I hear a lot when we're talking about latency and performance, and it's P99 or P999s. When you say that, what does that mean?
Latency, as we talked about earlier, can be an observation of how long something takes from the vantage point of the observer, right? Define it however you want, and we'll go with that. And P999, I think tail latencies is another, so it's a term related to P999, P99. So what happens is, especially in a larger scale setup, the average latency or the mean latency or the median even of how long something takes is not the most informative metric you should follow. And that goes back to another term I think we use a lot, which is service level SLA. So if we want the vast majority of requests to succeed within a certain amount of time, we're talking about service level SLA, right? We will say we want 99.9% of the requests to come back to us with a successful result in maybe 500 milliseconds. This maps naturally to tail latencies because anything that takes longer than that 500 millisecond is going to fail. So in this case, latency translates to success or failure, right? So when you have a lot of instances, naturally there's more variability in your environment. So often you will have one or more instances that just doesn't behave the same way as the rest of them. And that sort of eats into your success rate. And that's why we care about tail latency.
Tail latency are those outliers of the P99 or P999, right?
Tail latency, it generally means the slowest portion of all your requests and how long they take. Right? P99 means 1% of all your requests will take longer than this number. P999 means 0.1%. So 99.9 is what P999 means. So that means 0.1% of all your requests take longer than that.
Gil Tene, CTO of Azul, had this awesome kind of definition of tail latency that I loved. He said it's like eating a handful of peanuts and it's that one rotten peanut. That's all you remember is that one rotten peanut. So that's tail latency.
There was a really good article. I think it's on ACM Communications. There's a talk about tail at scale. I believe it's given by one of the chief architects at Amazon. Amazon also has an extremely large scale operation, right? So one thing is scale exacerbates tail latency because often when you fulfill a complex request, you go to multiple services. And those multiple services may need to fan out to many instances of the same service to get certain state. Like this is true with caching, right? If you need 10 keys, you're likely hitting 10 different servers to get those 10 keys back. So if any of those 10 keys return slowly, your overall request comes back slowly. So this very simple and easily understandable phenomenon, when you have a sufficiently large scale, translates to a huge performance problem because large operations means a much bigger surface area, a much bigger chance of hitting a slow path or a slow machine, which brings down the overall performance of your entire product or entire service.
All right, we've been dancing around talking about scale for a while. Let's jump in and talk about scale. So as I mentioned before, my experience, if I've got a slow server, I'll SSH into it and deal with it. At a handful of servers, that's fine. But the idea of troubleshooting and debugging thousands, tens of thousands of servers has got to be a very different performance experience. So what is it like, or what is the process when you're dealing with that number of servers for dealing with performance issues?
So I think when you have a few servers, it's perfectly fine to just simultaneously be observing all of them, right? You can grasp the entire scope and all the information that you are monitoring. When you have a much larger scale operation, the bottleneck becomes aggregating all that information into one place, because whoever is looking at the performance problem or the health of the system cannot simultaneously be looking at 10,000 instances. So this funneling of information from a very wide scope down to a single location is the bottleneck and is the difficulty of designing any monitoring or performance tracking infrastructure. So one thing I find interesting is earlier I was saying zooming in. Right? So when you have a very large operation, naturally you cannot be collecting everything all the time. It's easier to do that with a few instances. So what ends up happening is you're collecting very coarse information about every instance all the time, but you do want to get a lot more information about a specific host or a specific location in your system when you realize that's the problem area.
But you're aggregating before you send the data into the collection point, or you're aggregating at the collection point, or both?
There's a lot of debate around this, right? So in production, what has happened at Twitter is people always want more visibility, especially when they run into a performance issue. So generally, we do minutely reporting on metrics. When people see a micro incident, a micro spike, it could be a traffic spike that only lasted less than a second, but it could cause disruption in the service and could harm the health of the services and leads to all kinds of behaviors like service getting restarted or escalated to other services. But if you look at the minutely metrics, everything looks normal. Maybe you see a tiny bump, but that bump is not something you can actually alert on because it looks like any other bump, right? But a bump that happens within half a second is totally different from a bump that sort of smoothly elevated over the entire minute. These are very different problems by nature. So being able to differentiate something that's short and spiky and something that's long and smooth is the key to a lot of performance problems. But you cannot get that from minutely aggregation, so people ask for it. However, if you universally bump the granularity from minutely to secondly, suddenly you're collecting 60 times as much data as you otherwise would. And you know most of the time you don't care. Nobody's going to look at the chart once every second. So why are you doing that? And it's hugely expensive. Monitoring is very, very expensive when you are collecting a large number of metrics.
So what's the answer?
So the answer, I think, this is my personal opinion, is that we should aggregate a limited number of metrics at a coarse enough level that it's not a huge burden. The monitoring system shouldn't be more expensive than the service itself, right? That's sort of like the rule of thumb. However, I don't think that means we need to sacrifice visibility into finer grain activities. And the key there is, earlier we said aggregation, getting everything into a central place is the expensive part, is the technically challenging part. So how do you balance that? It turns out that maybe you don't have to aggregate everything. Maybe you just need enough information in the aggregation to tell you which instance is the suspect, right? That's all you need. And one thing that's nice about modern day hardware is we actually have so much memory and so much CPU and so much disk pretty much lying on every host. And those hosts are rarely running at capacity. These are sort of dormant resources that can be used for something good if we know how to tap into that without interfering with the main purpose of the workload.
So talk more about that. When you say you've got this dormant resources that you could use for good, what types of things are you talking about?
I'm talking about free, quote unquote, disk spaces that most people don't bother using. Right? When was the last time that a container ran out of disk space? Probably not very often. And this is something that when I was working on cache, I also relied very heavily on. So cache was actually when this idea sort of started, is that we only had minutely aggregation. We know cache is fairly often see small spikes of requests. So these are hotspots we call, and people want to learn about these hotspots. But how can we provide that information to them from cache? Right? One thing we did is we did this very high performance logging that captures a lot of information and dump those to disk in an asynchronous fashion so they don't interfere with the main serving. However, we bond our resources. We don't want to use up the entire disk, which can be easily done if you're logging everything. We say, when do people ask about performance issues? In fact, right after the performance problems happen, right? So what if we cache only a very short period of data? We don't need to cache something even for a full day in most cases. People come to us like 20 minutes after the incident happens. If we store information about these performance-related issues on the local disk, just keep them there for a short period of time, maybe a few hours, maybe a few days, depending on what you can afford. We can go back and apply analysis on these local repertoire of data, and we will get our answer. Right? Those information does not need to leave the box because performance issues are often edge cases and are isolated on a few places in your entire operation. So they're not everywhere. So we translate what is a large-scale monitoring problem into back to your previous example. If you have one or two machines, you can SSH into that and do whatever you want with whatever is locally available. And that's, I think, what we should do is we should just zoom in and dive in whatever is available there.
I got to ask, when you've got 10,000 servers, do you do that? Do you literally log into that one instance to see what was sick with it? Or do you just say, I'm going to cut my losses and cut it loose, and I've got 9,999 other servers to handle it?
We have to, because that one instance is what make our clients, what our users generate enough failures that they're violating their SLA, right? So we look at the minutely data. We say, oh, this one is interesting. It receives more traffic than the others on a minutely basis. So let's see whether it's all the requests in 1 second or spread out over a minute. In the latter case, it doesn't matter. In the former case, we have a problem. And that information is actually something the users or customers can act on, because if they know someone's accessing, say, Taylor Swift's tweet all the time, now they can start caching Taylor Swift's tweet somewhere else, maybe on their client, right? Then they remove the hotspot.
I love that. It's cool. All right. So I want to talk about some interesting problems maybe you've uncovered. So what are some interesting problems you've seen with performance at the scale? As I mentioned before, if I'm operating 10 servers or so and something happens 1 in a million times, I might see it once a year, but you might see it hundreds of times a day at the scale that you're operating at. What are some interesting problems you ran into?
One of my favorite was the DDoS incident we had. Ellen DeGeneres tweeted a selfie of herself and a bunch of other big stars having a good time at Oscars, and he encouraged her followers to retweet and favorite because they want to break a record on Twitter. And that actually broke Twitter.
Nice.
And the way they broke Twitter is through caching, surprisingly. They generated enough traffic that some of the services started timing out to one particular cache server that hosts that tweet. And as a response to all these requests, because when you have a lot of requests, only one server, the request started timing out. So what do you do when you time out? You retry. The one caveat there is before they retry, they actually also tear down the connection. Because when you time out, you don't know the state of the connection. You might as well start from a clean slate. So all the clients decided that they wanted to close all their existing connections and open new ones. And opening new connections turned out to be quite expensive. So when you have thousands of instances all trying to open multiple connections to one server at the exact same moment, this server just falls over. So it's not even that we couldn't serve the requests fast enough. We didn't even get to see the request after the first moment, because all we saw was a flood of open connection requests. And before we could accept all of them, they all got closed because more timeouts. So we got stuck in that loop for a while, and then we had to restart some machines.
So what was the retro on that? What did you do to prevent something from that in the future?
Actually, we did a number of things. One is we actually changed the behavior both on the client side and on the server side. On the server side, we're like, if we cannot accept these connections fast enough, we shouldn't even try, right? It's much better to tell clients to go away and handle the subset of connections that we actually can process in time. So that's resulted in a number of IP table rules that rate limits the number of connections that can reach the server, or by server, I mean the cache service instance. Everybody else, we just reject the connections right away, so the clients actually can do something else. On the client side, we also did major changes. We realized opening a lot of connections every time you see a timeout is kind of wasteful. A better strategy is to we want to treat request timeout differently from other connection health problems. What we ended up doing is we introduced the pipelining client. So we would reuse a client. So instead of opening multiple connections when we have multiple outstanding requests, we funnel them all through the same pipe. So that naturally cuts down the number of overall connection counts. Also, we decouple the request timeout behavior from other connection health issues. So when you have a request timeout, it doesn't necessarily result in a connection being reestablished. A combination of these two pretty much prevented similar problems from reoccurring. And that was the last time we saw this kind of incident.
Very nice. That's the day Ellen DeGeneres broke Twitter. When it comes to performance and fine-tuning, what do you think is the biggest problem today facing the industry and software developers?
I have beef with how a lot of people actually end up facing and try to solve, or at least are hunted by the same or very similar performance problems in their individual setups. But their scale means that it's not worth the time or effort for every individual to invest significantly into this. So as you said, if you have 2-3 machines, you see a performance problem maybe once a year. And you certainly don't want to spend 3 months out of your precious time that you could feature work into debugging that. But there are lots of people like that. So what ends up happening is smaller scale operations have to put up with all these corner cases or edge cases of performance issues, and hoping that people like Google or Facebook or maybe sometimes Twitter who have sufficient scale will see this often enough, and it will bother them enough that they decide they want to put the resources into solving these problems. However, if you look at the industry collectively, we can save a lot of collective time and energy if these problems are actually solved instead of just band-aided or ignored. So one thing that I really hope to see is there exists a community or mechanism to surface some of these common issues, and we can actually provide incentive or sometimes even reward for people to solve these problems for the community once and for all, so we can all do something else and something more interesting.
Very cool. I love the idea. It's almost like a bug bounty for performance.
Yeah.
Sounds interesting. All right, Yao, thank you for taking the time to chat with us. It was a lot of fun.
This is fun for me too. Thank you.